Well, welcome back to Lesson 4 in our study of the network layer. This is Networks and Distributed Systems based on the textbook by Jim Caros and Keith Ross, Computer Networking, a Top-Down Approach. We just concluded a discussion of two network architectures, a datagram and a virtual circuit. And now we're going to move on. So let's go. In this module, we'll explore how addressing and forwarding are done in the Internet. Internet addressing and forwarding are important components of the Internet Protocol, IP. There are two versions of IP in use today. First, there is the IP Protocol version 4, which is usually referred to simply as IPv4. We'll take a look at IP version 6, which has been proposed to replace IPv4 at the end of this section. First, let's consider the components that make up the Internet's network layer. As shown here in Figure 4.12, the Internet's network layer has three major components. The first component is the IP protocol. The second major component is the routing component, which determines the path a datagram follows from source to destination. We mentioned earlier that routing protocols compute the forwarding tables that are used to forward packets through the network. The final component of the network layer is a facility to report errors in datagrams and respond to requests for certain network layer information. This is Internet Control Message Protocol, abbreviated ICMP usually. Recall that a network layer packet is referred to as a datagram. IP version 4 datagram format is shown here in Figure 4.13. The key fields in the IPv4 datagram are the following. Version number. These 4 bits specify the IP protocol version of the datagram. By looking at the version number, the router can determine how to interpret the remainder of the IP datagram. Different versions of IP use different datagram formats. The datagram format for the current version of IP, IPv4, is shown here in Figure 4.13. Datagram format for the new IPv6 will be discussed at the end of this section. Header length. Because an IPv4 datagram can contain a variable number of options, which are included in the header, these 4 bits are needed to determine where in the IP datagram the data actually begins. Some IP datagrams do not contain options, so the typical IP datagram has a 1200 byte header. Type of service. The type of service bits were included in IPv4 header to allow different types of datagrams. For example, those that require slow delay or high throughput or reliability to be distinguished from each other. For example, it might be useful to distinguish real-time datagrams, like those used by IP telephony, from non-real-time traffic, for example, FTP. The specific level of service to be provided is a policy issue determined by the router's administrator. Datagram length. This is the total length of the IP datagram. That's the header plus the data, measured in bytes. Since this field is 16 bits long, the theoretical maximum size of an IP datagram is 65,535. However, datagrams are rarely larger than 1500 bytes. Identifier, flags, fragmentation offset. These 3 fields have to do with so-called IP fragmentation, a topic that we'll discuss shortly. Interestingly, the new version of IP, IPv6, does not allow for fragmentation at routers. Time to live. The time to live field is included to ensure that datagrams do not circulate forever. For example, if one is caught in a long-lived routing loop. This field is decremented by 1 each time the datagram is processed by a router. If the time to live field reaches 0, the data must be dropped. Protocol. This field is only used when an IP datagram reaches its final destination. The value of this field indicates the specific transport layer protocol to which the data portion of this datagram should be passed. For example, a value of 6 indicates the data portion is to be passed to TCP, while a value of 17 indicates the data is to be passed to UDP. For a list of all possible values, you can see INA protocol numbers 2012. Note that the protocol number in the IP datagram has a role that is analogous to the role of the port number field in the transport layer segment. The protocol number is the glue that holds the network and transport layers together, whereas the port number field is the glue that binds the transport and application layers together. Header checksum. The header checksum aids a router in detecting bit errors in a received IP datagram. The header checksum is computed by treating each 2 bytes in the header as a number and summing these numbers using ones complement arithmetic. The ones complement of this sum, known as the internet checksum, is stored in the checksum field. A router computes the header checksum for each received IP datagram and detects an error condition if the checksum carried in the datagram header does not equal the computed checksum. Routers typically discard datagrams for which an error has been detected. Note the checksum must be recomputed and stored again at each router, like the time to live field, and possibly the options field as well may change. A question often asked at this point is, why does TCP/IP perform error checking at both the transport and the network layers? There are several reasons for this repetition. First, note that only the IP header is checksummed at the IP layer, while the TCP/UDP checksum is computed over the entire TCP/UDP segment. Second, TCP/UDP and IP do not necessarily both have to belong to the same protocol stack. TCP can, in principle, run over different protocols, for example ATM. And IP can carry data that will not be passed to TCP/UDP. Source and destination addresses. When a source creates a datagram, it inserts its IP address into the source IP's address field and inserts the address of the ultimate destination into the destination IP address field. Often the source determines the destination via a DNS lookup that we talked about earlier. Options. The options fields allow a header IP to be extended. Header options were meant to be used rarely. Hence the decision to save overhead by not including the information in option fields in every datagram header. Some datagrams may require options processing and others may not. The amount of time needed to process an IP datagram at the router can vary greatly. These considerations become particularly important for IP processing in high-performance routers and hosts. For these reasons and others, IP options were dropped in the IPv6 header. Data, that's the payload of the datagram. Finally, we come to the last and most important field. In most circumstances, the data field of the IP datagram contains the transport segment, either TCP or UDP, to be delivered to the destination. However, the data field can carry other types of data, such as an ICMP message. Note that an IP datagram has a total of 20 bytes of header, assuming no options. If the datagram carries a TCP segment, then each non-fragmented datagram carries a total of 40 bytes of header, 20 bytes of IP header plus 20 bytes of TCP header, along with the application layer message. Remember that each layer of the TCP/IP model takes the data from above and adds its own header to the data and passes it on. Well, this is a good place to stop and catch your breath. Take whatever time you need to go back over your notes and review and fill out your study guide. And when you're ready to come back, we'll start a new one.